The turbofan or fanjet is a type of air-breathing jet engine that finds wide use in aircraft propulsion. The word turbofan is a portmanteau of turbine, and fan. The turbo portion refers to a gas turbine engine which takes mechanical energy from combustion, and the fan, a ducted fan that uses the mechanical energy from the gas turbine to accelerate air rearwards. Thus, whereas all the air taken in by a turbojet passes through the turbine, in a turbofan some of that air bypasses the turbine. A turbofan thus can be thought of as a turbojet being used to drive a ducted fan, with both of those contributing to the thrust. The ratio of the mass flow of air bypassing the engine core compared to the mass flow of air passing through the core is referred to as the bypass ratio. The engine produces thrust through a combination of these two portions working in concert. Engines that use more jet thrust relative to fan thrust are known as low bypass turbofans. Conversely, those that have considerably more fan thrust than jet thrust are known as high bypass. Most commercial aviation jet engines in use today are of the high bypass type, and most modern military fighter engines are low bypass. Afterburners are not used on high bypass turbofan engines but may be used on either low bypass turbofan or turbojet engines. Most of the airflow through a high bypass turbofan is low velocity bypass flow. Even when combined with the much higher velocity engine exhaust, the net average exhaust velocity is considerably lower than in a pure turbojet. Engine noise is largely a function of exhaust velocity, therefore turbofan engines are significantly quieter than a pure jet of the same thrust. Other factors include turbine blade and exhaust outlet geometries, such as noise-reducing chevrons seen on the Rolls-Royce Trent 1000 and General Electric Genx engines used on the Boeing 787. Since the efficiency of propulsion is a function of the relative airspeed of the exhaust to the surrounding air, propellers are most efficient for low speed, pure jets for high speeds, and ducted fans in the middle. Turbofans are thus the most efficient engines in the range of speeds from about 500 to 1000 km/h. The speed at which most commercial aircraft operate. Turbofans retain an efficiency edge over pure jets at low supersonic speeds up to roughly Mach 1.6, but have also been found to be efficient when used with continuous afterburner at Mach 3 and above. The vast majority of turbofans follow the same basic design, with a large fan at the front of the engine and a relatively small jet engine behind it. There have been a number of variations on this design, however, including rear-mounted fans which can easily be added to an existing pure jet design, or designs that combine a low-pressure turbine and a fan stage in a single rear-mounted unit. Introduction: the turbofan is a derivative of the turbojet engine. In a turbojet, air undergoes four main phases, a process known as the Brayton Cycle, a compression phase in a compressor, approximately adiabatic, where its pressure and temperature increase. A heating phase in a combustor, where its temperature and volume increase at approximately constant pressure. An expansion phase in a turbine, approximately adiabatic, where mechanical work is extracted from the air to power the compressor. A further expansion phase in a nozzle, where its speed increases as it returns to inlet pressure. Thrust is provided by the difference in speed between the outlet and inlet. It is important to note that in a turbojet the compressor and turbine taken together form a nearly net-zero mechanical energy system, that is nearly all the mechanical shaft power produced by the turbine is consumed by the compressor, with only a small remainder taken away to drive accessory systems such as electrical alternators or hydraulic system pumps. Neglecting these accessory systems, the net propulsive output of a turbojet is not shaft power, instead it is the kinetic energy of the jet exhaust itself. Although the expansion process in the turbine reduces the gas pressure, there remains considerable thermal energy and pressure in the gases leaving the turbine. These energy forms are partly converted into kinetic energy by expansion to ambient pressure through a propelling nozzle, forming a high-velocity flow which provides reactive propulsion. After World War II, two-spool turbojets were developed to make it easier to throttle back compression systems with a high design overall pressure ratio. Adopting the two-spool arrangement enables the compression system to be split in two, with a low-pressure compressor supercharging a high-pressure compressor. Each compressor is mounted on a separate shaft, driven by its own turbine. Otherwise, a two-spool turbojet is much like a single-spool engine. Modern turbofans evolved from the two-spool axial flow turbojet engine, essentially by increasing the relative size of the low-pressure compressor to the point where some of the air exiting the unit actually bypasses the coarse stream passing through the main combustor. Civil aviation high-bypass turbofans usually have a single large fan disc, whereas most military aviation low-bypass turbofans have multi-disc compressors as a compromise between greater power-to-weight ratios, supersonic performance, and the capability of using afterburners, versus the higher fuel economy of a high-bypass design. Modern military transport turbofan engines are virtually identical to their civilian counterparts. Turboprop engines are gas turbine engines that deliver almost all of their power to a shaft to drive a propeller. Turboprops remain popular on very small or slow aircraft, such as small commuter airliners, for their fuel efficiency at lower speeds, as well as on medium military transports and patrol planes, such as the C-130 Hercules and P-3 Orion, for their high takeoff performance and mission endurance benefits. Like reciprocating propeller engines, turboprops can be used with controllable pitch propellers which allow thrust to be adjusted independently of the engine rotation speed. If the turboprop is better at moderate flight speeds and the turbojet is better at very high speeds, it might be imagined that at some speed range in the middle a mixture of the two is best. Such an engine is the turbofan. Another name sometimes used is ducted fan, though that term is also used for propellers and fans used in vertical flight applications. The difference between a turbofan and a propeller, besides direct thrust, is that the intake duct of the former slows the air before it arrives at the fan face. As both propeller and fan blades must operate at subsonic inlet velocities to be efficient, ducted fans allow efficient operation at higher vehicle speeds. Some large modern turbofans, like the Trent, have blade tip speeds at 1,730 km/h. Depending on specific thrust, ducted fans operate best from about 400 to 2,000 km/h, which is why turbofans are the most common type of engine for aviation used today are Euro and airliners as well as in subsonic and supersonic military fighter and trainer aircraft. It should be noted, however, that turbofans use extensive ducting to force incoming air to subsonic velocities. Bypass ratio is a parameter often used for classifying turbofans. When the low-bypass Conway engine entered service in 1960, no one even called it a turbofan, the term first being applied to Pratt & Whitney's JT3D with its 1-to-1 bypass. The noise of any type of jet engine is strongly related to the velocity of the exhaust gases, typically being proportional to the eighth power of the jet velocity. High bypass ratio turbofans are relatively quiet compared to turbojets and low bypass ratio turbofans. A low specific thrust engine has a low jet velocity by definition, as the following approximate equation for net thrust implies. Where intake mass flow, fully expanded jet velocity, aircraft flight velocity, rearranging the above equation, specific thrust is given by. So for zero flight velocity, specific thrust is directly proportional to jet velocity. Relatively speaking, low specific thrust engines are large in diameter to accommodate the high airflow required for a given thrust. Although jet aircraft are loud, a conventional piston engine or a turboprop engine delivering the same thrust would be much louder. Early turbofans, early turbojet engines were very fuel inefficient, as their overall pressure ratio and turbine inlet temperature were severely limited by the technology available at the time. The very first running turbofan was the German Daimler-Benz DB670, which was operated on its testbed on April 1, 1943. The engine was abandoned later while the war went on and problems could not be solved. The British wartime Mitrovic F2 axial flow jet was given a fan, as the Mitrovic F3 in 1943, to create the first British turbofan. Improved materials, and the introduction of twin compressors such as in the Bristol Olympus and the later Pratt & Whitney JT3C engine, increased the overall pressure ratio and thus the thermodynamic efficiency of engines, but they also led to a poor propulsive efficiency. as pure turbojets have a high specific thrust high-velocity exhaust better suited to supersonic flight. The original low-bypass turbofan engines were designed to improve propulsive efficiency by reducing the exhaust velocity to a value closer to that of the aircraft. The Rolls-Royce Conway, the world's first production turbofan, had a bypass ratio of 0.3, similar to the modern General Electric F404 fighter engine. Civilian turbofan engines of the 1960s, such as the Pratt & Whitney JT8D and the Rolls-Royce Spey, had bypass ratios closer to 1, but were not dissimilar to their military equivalents. The unusual General Electric CF700 turbofan engine was developed as an aft fan engine with a 2.0 bypass ratio. This was derived from the General Electric J85/CJ610 turbojet to power the larger Rockwell Sabreliner 75/80 model aircraft, as well as the Dassault Falcon 20 with about a 50% increase in thrust. The CF700 was the first small turbofan in the world to be certified by the Federal Aviation Administration. There are now over 400 CF700 aircraft in operation around the world, with an experience base of over 10 million service hours. The CF700 turbofan engine was also used to train moon-bound astronauts in Project Apollo as the power plant for the Lunar Landing Research Vehicle. The CJ805-23 was a similar, but larger, design. Low-bypass turbofan. A high-specific thrust low-bypass ratio turbofan normally has a multi-stage fan, developing a relatively high pressure ratio and, thus, yielding a high exhaust velocity. The core airflow needs to be large enough to give sufficient core power to drive the fan. A smaller core flow higher bypass ratio cycle can be achieved by raising the turbine rotor inlet temperature. Imagine a retrofit situation where a new low bypass ratio, mixed exhaust, turbofan is replacing an old turbojet, in a particular military application. Say the new engine is to have the same airflow and net thrust as the one it is replacing. A bypass flow can only be introduced if the turbine inlet temperature is allowed to increase, to compensate for a correspondingly smaller core flow. Improvements in turbine cooling material technology would facilitate the use of a higher turbine inlet temperature, despite increases in cooling air temperature, resulting from a probable increase in overall pressure ratio. Efficiently done, the resulting turbofan would probably operate at a higher nozzle pressure ratio than the turbojet, but with a lower exhaust temperature to retain net thrust. Since the temperature rise across the whole engine would be lower, the fuel flow would also be reduced, resulting in a better specific fuel consumption. A few low bypass ratio military turbofans have variable inlet guide vanes, with piano-style hinges, to direct air onto the first rotor stage. This improves the fan surge margin in the mid-flow range. The Swingwing F-111 achieved a very high range payload capability by pioneering this, and it was also the heart of the famous F-14 Tomcat air superiority fighter, which used the same engines in a smaller, more agile airframe to achieve efficient cruise and Mach 2 speed. Afterburning turbofan. Since the 1970s, most jet fighter engines have been low-medium bypass turbofans with a mixed exhaust, afterburner and variable area final nozzle. An afterburner is a combustor located downstream of the turbine blades and directly upstream of the nozzle, which burns fuel from afterburner-specific fuel injectors. When lit, prodigious amounts of fuel are burnt in the afterburner, raising the temperature of exhaust gases by a significant degree, resulting in a higher exhaust velocity engine-specific thrust. The variable geometry nozzle must open to a larger throat area to accommodate the extra volume flow when the afterburner is lit. Afterburning is often designed to give a significant thrust boost for takeoff, transonic acceleration and combat maneuvers, but is very fuel-intensive. Consequently, afterburning can only be used for short portions of a mission. Unlike the main combustor, where the downstream turbine blades must not be damaged by high temperatures, an afterburner can operate at the ideal maximum temperature. At a fixed total applied fuel-air ratio, the total fuel flow for a given fan airflow will be the same, regardless of the dry specific thrust of the engine. However, a high specific thrust turbofan will, by definition, have a higher nozzle pressure ratio, resulting in a higher afterburning net thrust and, therefore, a lower afterburning specific fuel consumption. However, high specific thrust engines have a high dry SFC. The situation is reversed for a medium specific thrust afterburning turbofan, that is, poor afterburning SFC, good dry SFC. The former engine is suitable for a combat aircraft which must remain in afterburning combat for a fairly long period, but only has to fight fairly close to the airfield. The latter engine is better for an aircraft that has to fly some distance, or loiter for a long time, before going into combat. However, the pilot can only afford to stay in afterburning for a short period, before aircraft fuel reserves become dangerously low. Modern low-bypass military turbofans include the Pratt & Whitney F119, the Eurojet EJ200, the General Electric F110, the Plymouth Road 33, and the Saturn AL31, all of which feature a mixed exhaust, afterburner and variable area propelling nozzle. High bypass turbofan. The low specific thrust high bypass ratio turbofans used in today's civil jetliners evolved from the high specific thrust low bypass ratio turbofans used in such production aircraft back in the 1960s. Low specific thrust is achieved by replacing the multi-stage fan with a single-stage unit. Unlike some military engines, modern civil turbofans do not have any stationary inlet guide vanes in front of the fan rotor. The fan is scaled to achieve the desired net thrust. The core of the engine must generate sufficient core power to at least drive the fan at its design flow and pressure ratio. Through improvements in turbine cooling material technology, a higher turbine rotor inlet temperature can be used, thus facilitating a smaller core and improving the core thermal efficiency. Reducing the core mass flow tends to increase the load on the LP turbine, so this unit may require additional stages to reduce the average stage loading and to maintain LP turbine efficiency. Reducing core flow also increases bypass ratio. Further improvements in core thermal efficiency can be achieved by raising the overall pressure ratio of the core. Improved blade aerodynamics reduces the number of extra compressor stages required. With multiple compressors, dramatic increases in overall pressure ratio have become possible. Variable geometry enable high pressure ratio compressors to work surge-free at all throttle settings. The first high bypass turbofan engine was the General Electric TF-39, designed in mid-1960s to power the Lockheed C-5 Galaxy military transport aircraft. The civil General Electric CF-6 engine used a derived design. Other high bypass turbofans are the Pratt & Whitney JT9D, the three-shaft Rolls-Royce RB211 and the Cfm International Cfm 56. Also the smaller TF-34. More recent large high bypass turbofans include the Pratt & Whitney Palais 4000, the three-shaft Rolls-Royce Trent, the General Electric GE90/Genx and the GP7000, produced jointly by GE and P&W. For reasons of fuel economy, and also of reduced noise, almost all of today's jet airliners are powered by high bypass turbofans. Although modern combat aircraft tend to use low bypass ratio turbofans, military transport aircraft mainly use high bypass ratio turbofans for fuel efficiency. Because of the implied low mean jet velocity, a high bypass ratio low specific thrust turbofan has a high thrust lapse rate. Consequently, the engine must be oversized to give sufficient thrust during climb cruise at high flight speeds. Because of the high thrust lapse rate, the static thrust is relatively high. This enables heavily laden, wide-body aircraft to accelerate quickly during takeoff and consequently lift off within a reasonable runway length. The turbofans on twin-engined airliners are further oversized to cope with losing one engine during takeoff, which reduces the aircraft's net thrust by 50%. Modern twin-engined airliners normally climb very steeply immediately after takeoff. If one engine is lost, the climb out is much shallower, but sufficient to clear obstacles in the flight path. The Soviet Union's engine technology was less advanced than the West's, and its first wide-body aircraft, the Ilyushin Il-86, was powered by low-bypass engines. The Yakovlev Yak-42, a medium-range, rear-engined aircraft seating up to 120 passengers introduced in 1980 was the first Soviet aircraft to use high-bypass engines. Turbofan configurations. Turbofan engines come in a variety of engine configurations. For a given engine cycle, the choice of turbofan configuration has little impact upon the design point performance, as long as overall component performance is maintained. Off-design performance and stability is, however, affected by engine configuration. As the design overall pressure ratio of an engine cycle increases, it becomes more difficult to throttle the compression system, without encountering an instability known as compressor surge. This occurs when some of the compressor aerofoils stall, causing a violent change in the direction of the airflow. However, compressor stall can be avoided, at throttled conditions, by progressively, 1. Opening interstage intercompressor blow-off valves, and or, 2. Closing variable stators within the compressor. Most modern American civil turbofans employ a relatively high pressure ratio high-pressure compressor, with many rows of variable stators to control surge margin at part throttle. In the 3-spool RB211/Trent, the core compression system is split into two, with the IP compressor, which supercharges the HP compressor, being on a different coaxial shaft and driven by a separate turbine. As the HP compressor has a modest pressure ratio, it can be throttled back surge-free, without employing variable geometry. However, because a shallow IP compressor working line is inevitable, the IPC has one stage of variable geometry on all variants except the -535, which has none. Single-shaft turbofan. Although far from common, the single-shaft turbofan is probably the simplest configuration, comprising a fan and high-pressure compressor driven by a single turbine unit, all on the same shaft. The Snecma M53, which powers Mirage fighter aircraft, is an example of a single-shaft turbofan. Despite the simplicity of the turbomachinery configuration, the M53 requires a variable area mixer to facilitate part throttle operation. Aft fan turbofan. One of the earliest turbofans was a derivative of the General Electric J79 turbojet, known as the CJ805-23, which featured an integrated aft fan low-pressure turbine unit located in the turbojet exhaust jet pipe. Hot gas from the turbojet turbine exhaust expanded through the LP turbine, the fan blades being a radial extension of the turbine blades. This aft fan configuration was later exploited in the General Electric GE36UDF demonstrator of the early 80s. One of the problems with the aft fan configuration is hot gas leakage from the LP turbine to the fan. Basic two-spool. Many turbofans have the basic two-spool configuration where both the fan and LP turbine are mounted on a second shaft, running concentrically with the HP spool. The branch 710 is typical of this configuration. At the smaller thrust sizes, instead of all-axial blading, the HP compressor configuration may be axial centrifugal, double centrifugal or even diagonal centrifugal. Boosted two-spool. Higher overall pressure ratios can be achieved by either raising the HP compressor pressure ratio or adding an intermediate pressure compressor between the fan and HP compressor, to supercharge or boost the latter unit, helping to raise the overall pressure ratio of the engine cycle to the very high levels employed today. All of the large American turbofans feature an IP compressor mounted on the LP shaft and driven, like the fan, by the LP turbine, the mechanical speed of which is dictated by the tip speed and diameter of the fan. The Rolls-Royce Branch 715 is a non-American example of this. The high bypass ratios used in modern civil turbofans tends to reduce the relative diameter of the attached IP compressor, causing its mean tip speed to decrease. Consequently, more IPC stages are required to develop the necessary IPC pressure rise. 3-spool. Rolls-Royce chose a 3-spool configuration for their large civil turbofans, where the intermediate pressure compressor is mounted on a separate shaft, running concentrically with the LP and HP shafts, and is driven by a separate IP turbine. The first 3-spool engine was the earlier Rolls-Royce RB203 Trent of 1967. Ivchenko Design Bureau chose the same configuration for their Lotarev D36 engine, followed by Lotareve Progress D18T and Progress D436. The Turbo Union a B199 military turbofan also has a 3-spool configuration, as do the military kits of NK25 and NK321. Geared fan. As bypass ratio increases, the mean radius ratio of the fan and low-pressure turbine increases. Consequently, if the fan is to rotate at its optimum blade speed, the LPT blading will spin slowly, so additional LPT stages will be required to extract sufficient energy to drive the fan. Introducing a reduction gearbox, with a suitable gear ratio, between the LP shaft and the fan enables both the fan and LP turbine to operate at their optimum speeds. Typical of this configuration are the long-established Honeywell TFE731, the Honeywell ALF 502/507, and the recent Pratt & Whitney Palais 1000G. Military turbofans. Most of the configurations discussed above are used in civilian turbofans, while modern military turbofans are usually basic 2-spool. High-pressure turbine. Most civil turbofans use a high-efficiency, 2-stage HP turbine to drive the HP compressor. The CFM 56 uses an alternative approach, a single-stage, high-work unit. While this approach is probably less efficient, there are savings on cooling air, weight and cost. In the RB211 and Trent series, Rolls-Royce split the 2 stages into 2 discrete units. One on the HP shaft driving the HP compressor. The other on the IP shaft driving the IP compressor. Modern military turbofans tend to use single-stage HP turbines. Low-pressure turbine. Modern civil turbofans have multi-stage LP turbines. The number of stages required depends on the engine cycle bypass ratio and how much supercharging is on the LP shaft, behind the fan. A geared fan may reduce the number of required LPT stages in some applications. Because of the much lower bypass ratios employed, military turbofans only require 1 or 2 LP turbine stages. Cycle improvements. Consider a mixed turbofan with a fixed bypass ratio and airflow. Increasing the overall pressure ratio of the compression system raises the combustor entry temperature. Therefore, at a fixed fuel flow there is an increase in turbine rotor inlet temperature. Although the higher temperature rise across the compression system implies a larger temperature drop over the turbine system, the mixed nozzle temperature is unaffected, because the same amount of heat is being added to the system. There is, however, a rise in nozzle pressure, because overall pressure ratio increases faster than the turbine expansion ratio, causing an increase in the hot mixer entry pressure. Consequently, net thrust increases, whilst specific fuel consumption decreases. A similar trend occurs with unmixed turbofans. So turbofans can be made more fuel efficient by raising overall pressure ratio and turbine rotor inlet temperature in unison. However, better turbine materials and/or improved vane blade cooling are required to cope with increases in both turbine rotor inlet temperature and compressor delivery temperature. Increasing the latter may require better compressor materials. Overall pressure ratio can be increased by improving fan LP compressor pressure ratio and/or HP compressor pressure ratio. If the latter is held constant, the increase in compressor delivery temperature implies an increase in HP mechanical speed. However, stressing considerations might limit this parameter, implying, despite an increase in overall pressure ratio, a reduction in HP compressor pressure ratio. According to simple theory, if the ratio turbine rotor inlet temperature / HP, compressor delivery temperature is maintained, the HP turbine throat area can be retained. However, this assumes that cycle improvements are obtained, while retaining the datum compressor exit flow function. In practice, changes to the non-dimensional speed of the compressor and cooling bleed extraction would probably make this assumption invalid, making some adjustment to HP turbine throat area unavoidable. This means the HP turbine nozzle guide vanes would have to be different from the original. In all probability, the downstream LP turbine nozzle guide vanes would have to be changed anyway. Thrust growth. Thrust growth is obtained by increasing core power. There are 2 basic routes available: hot route, increase HP turbine rotor inlet temperature, cold route, increase core mass flow. Both routes require an increase in the combustor fuel flow and, therefore, the heat energy added to the core stream. The hot route may require changes in turbine blade vane materials and/or better blade vane cooling. The cold route can be obtained by one of the following: adding T stages to the LPIP compression, adding a zero stage to the HP compression, improving the compression process, without adding stages, all of which increase both overall pressure ratio and core airflow. Alternatively, the core size can be increased, to raise core airflow, without changing overall pressure ratio. This route is expensive, since a new turbine system is also required. Changes must also be made to the fan to absorb the extra core power. On a civil engine, jet noise considerations mean that any significant increase in takeoff thrust must be accompanied by a corresponding increase in fan mass flow. To reduce noise, civilian turbofans have a specially shaped nozzle that limits the exhaust speed to subsonic speeds. This leads to a thermic clogging termed choked nozzle where the mass flow cannot be increased beyond a certain amount. Thus, the mass flow can only be increased through the bypass airstream, usually by increasing fan diameter. On military engines, the fan pressure ratio would probably be increased to improve specific thrust, jet noise not normally being an important factor. Technical discussion: specific thrust is an important parameter for turbofans and jet engines in general. Imagine a fan operating within a pipe, which is connected to a propelling nozzle. It is fairly obvious, the higher the fan pressure ratio, the higher the jet velocity and the corresponding specific thrust. Now imagine we replace this setup with an equivalent turbofan, same airflow and same fan pressure ratio. Obviously, the core of the turbofan must produce sufficient power to drive the fan via the low-pressure turbine. If we choose a low turbine inlet temperature for the gas generator, the core airflow needs to be relatively high to compensate. The corresponding bypass ratio is therefore relatively low. If we raise the turbine inlet temperature, the core airflow can be smaller, thus increasing bypass ratio. Raising turbine inlet temperature tends to increase thermal efficiency and, therefore, improve fuel efficiency. Naturally, as altitude increases there is a decrease in air density and, therefore, the net thrust of an engine. There is also a flight speed effect, termed thrust lapse rate. Consider the approximate equation for net thrust again. With a high specific thrust engine, the jet velocity is relatively high, so intuitively one can see that increases in flight velocity have less of an impact upon net thrust than a medium specific thrust engine, where the jet velocity is lower. The impact of thrust lapse rate upon a low specific thrust engine is even more severe. At high flight speeds, high specific thrust engines can pick up net thrust through the ram rise in the intake, but this effect tends to diminish at supersonic speeds because of shock wave losses. Thrust growth on civil turbofans is usually obtained by increasing fan airflow, thus preventing the jet noise becoming too high. However, the larger fan airflow requires more power from the core. This can be achieved by raising the overall pressure ratio to induce more airflow into the core and by increasing turbine inlet temperature. Together, these parameters tend to increase core thermal efficiency and improve fuel efficiency. Some high bypass ratio civil turbofans use an extremely low area ratio, convergent-divergent, nozzle on the bypass stream, to control the fan working line. The nozzle acts as if it has variable geometry. At low flight speeds the nozzle is unchoked, so the exhaust gas speeds up as it approaches the throat and then slows down slightly as it reaches the divergent section. Consequently, the nozzle exit area controls the fan match and, being larger than the throat, pulls the fan working line slightly away from surge. At higher flight speeds, the ram rise in the intake increases nozzle pressure ratio to the point where the throat becomes choked. Under these circumstances, the throat area dictates the fan match and, being smaller than the exit, pushes the fan working line slightly towards surge. This is not a problem, since fan surge margin is much better at high flight speeds. The off-design behavior of turbofans is illustrated under compressor map and turbine map. Because modern civil turbofans operate at low specific thrust, they only require a single fan stage to develop the required fan pressure ratio. The desired overall pressure ratio for the engine cycle is usually achieved by multiple axial stages on the core compression. Rolls-Royce tend to split the core compression into two with an intermediate pressure supercharging the HP compressor, both units being driven by turbines with a single stage, mounted on separate shafts. Consequently, the HP compressor need only develop a modest pressure ratio. U.S. civil engines use much higher HP compressor pressure ratios and tend to be driven by a two-stage HP turbine. Even so, there are usually a few IP axial stages mounted on the LP shaft, behind the fan, to further supercharge the core compression system. Civil engines have multi-stage LP turbines, the number of stages being determined by the bypass ratio, the amount of IP compression on the LP shaft and the LP turbine blade speed. Because military engines usually have to be able to fly very fast at sea level, the limit on HP compressor delivery temperature is reached at a fairly modest design overall pressure ratio, compared with that of a civil engine. Also, the fan pressure ratio is relatively high, to achieve a medium to high specific thrust. Consequently, modern military turbofans usually only have 5 or 6 horsepower compressor stages and only require a single-stage HP turbine. Low bypass ratio military turbofans usually have one LP turbine stage, but higher bypass ratio engines need 2 stages. In theory, by adding IP compressor stages, a modern military turbofan HP compressor could be used in a civil turbofan derivative, but the core would tend to be too small for high-thrust applications. Recent developments in blade technology, the turbine blades in a turbofan engine are subject to high heat and stress, and require special fabrication. New material construction methods and material science have allowed blades, which were originally polycrystalline, to be made from lined-up metallic crystals and more recently monocrystalline blades, which can operate at higher temperatures with less distortion. Nickel-based superalloys are used for HP turbine blades in almost all modern jet engines. The temperature capabilities of turbine blades have increased mainly through 4 approaches: the manufacturing process, cooling path design, thermal barrier coating, and alloy development. Although turbine blade materials have improved over the years, much of the increase in turbine inlet temperatures is due to improvements in blade vane cooling technology. Relatively cool air is bled from the compression system, bypassing the combustion process, and enters the hollow blade or vane. The gas temperature can therefore be even higher than the melting temperature of the blade. After picking up heat from the blade vane, the cooling air is dumped into the main gas stream. If the local gas temperatures are low enough, downstream blades vanes are uncooled and not adversely affected. Strictly speaking, cycle-wise the HP turbine rotor inlet temperature is more important than the turbine inlet temperature. Although some modern military and civil engines have peak RITs of the order of 1560 AA°C, such temperatures are only experienced for a short time on civil engines. Turbofan engine manufacturers. The turbofan engine market is dominated by General Electric, Rolls-Royce plc and Pratt & Whitney, in order of market share. GE and Snecma of France have a joint venture, Cfm International, which, as the third largest manufacturer in terms of market share, fits between Rolls-Royce and Pratt & Whitney. Rolls-Royce and Pratt & Whitney also have a joint venture, International Aero Engines, specializing in engines for the Airbus A320 family. Pratt & Whitney and General Electric have a joint venture, Engine Alliance, marketing a range of engines for aircraft such as the Airbus A380, while finally, Williams International markets a range of engines for the light jet market and cruise missiles. General Electric. GE Aviation, part of the General Electric conglomerate, currently has the largest share of the turbofan engine market. Some of their engine models include the CF6, GE90 and Genx engines. On the military side, GE engines power many U.S. military aircraft, including the F-110, powering 80% of the U.S. Air Force's F-16 Fighting Falcons, and the F-404 and F-414 engines, which power the Navy's FA-18 Hornet and Super Hornet. Rolls-Royce and General Electric were jointly developing the F-136 engine to power the Joint Strike Fighter, however, due to government budget cuts, the program has been eliminated. Rolls-Royce plc is the second largest manufacturer of turbofans and is most noted for their B211 and Trent series, as well as their joint venture engines for the Airbus A320 and McDonnell Douglas MD-90 families, the Panavia Tornado and the Boeing 717. The Rolls-Royce Armed Forces Europe, 3007, developed by Allison Engine Company before its acquisition by Rolls-Royce, powers several Embraer regional jets. Rolls-Royce Trent 970s were the first engines to power the new Airbus A380. The famous thrust-vectoring Pegasus, actually a Bristol Siddeley design taken on by Rolls-Royce when they took over that company, is the primary power plant of the Harrier jump jet, and its derivatives. Pratt & Whitney is third behind GE and Rolls-Royce in market share. The JT9D has the distinction of being chosen by Boeing to power the original Boeing 747 jumbo jet. The Pilot 4000 series is the successor to the JT9D, and powers some Airbus A310, Airbus A300, Boeing 747, Boeing 767, Boeing 777, Airbus A330 and MD-11 aircraft. The Pilot 4000 is certified for 180-minute ETOPS when used in twin jets. The first family has a 94-inch fan diameter and is designed to power the Boeing 767, Boeing 747, MD-11, and the Airbus A300. The second family is the 100-inch fan engine developed specifically for the Airbus A330 twin jet, and the third family has a diameter of 112-inch designed to power Boeing 777. The Pratt & Whitney F-119 and its derivative, the F-135, power the United States Air Force's F-22 Raptor and the International F-35 Lightning II, respectively. Rolls-Royce are responsible for the lift fan which will provide the F-35B variants with the STOVL capability. The F-100 engine was first used on the F-15 Eagle and F-16 Fighting Falcon. Newer Eagles and Falcons also come with GE F-110 as an option, and the two are in competition. Cfm International is a joint venture between GE Aircraft Engines and Snecma of France. They have created the very successful CFM 56 series, used on Boeing 737, Airbus A340, and Airbus A320 family aircraft. Williams International is a manufacturer of small gas turbine engines based in Walled Lake, Michigan, United States. It produces jet engines for cruise missiles and small jet-powered aircraft. They have been producing engines since the 1970s and the range produces between 1,000 and 3,600 pounds of thrust. The engines are used as original equipment on the Cessna Citation jet CJ1 through CJ4 and Cessna Mustang, Beechcraft 400 XP and Premier 1A, and there are several development programs with other manufacturers. The range is also very popular with the re-engine market being used by Sierra Jet and Nexton to breathe new life into aging platforms. Aviadvigatl is a Russian manufacturer of aircraft engines that succeeded the Soviet Soloviev Design Bureau. The company currently offers several versions of the Aviadvigatl PS90 engine that powers Ilyushin Il-96-30040T, Tupolev Tu-204, Tu-214 series and the Ilyushin Il-76 MD-90. The company is also developing the new Aviadvigatl PD-14 engine for the new Russian Mis-21 airliner. Ivchenko Progress is the Ukrainian aircraft engine company that succeeded the Soviet Ivchenko Design Bureau. Some of their engine models include Progress D-436 available on the Antonov in 72/74, Yakovlev Yak-42, Beery FB-200, Antonov in 148 and Tupolev Tu-334 and Progress D-18T that powers two of the world's largest airplanes, Antonov in 124 and Antonov in 225. Chinese turbofan manufacturers. 3 Chinese corporations build turbofan engines. Some of these are licensed or reverse-engineered versions of European and Russian turbofans, and the other are indigenous models, but all are in development phase. Shenyang Aircraft Corporation, Xi'an Aero Engine Corporation, Guizhou Aircraft Industry Corporation, Japanese turbofan manufacturers. 2 Japanese corporations build turbofan engines. One of these is Mitsubishi Heavy Industries, that manufactured under license the Pratt & Whitney JT8D turbofan for the Kawasaki C-1 military transport aircraft. The other is IHI Corporation, that manufactured various turbofan engines. NPO Saturn is the manufacturer of the Saturn AL-31 turbofan. Klimoth is the manufacturer of the Klimoth Road 33 turbofan. Extreme bypass jet engines. In the 1970s, Rolls-Royce Snecma tested a M45 SDO2 turbofan fitted with variable pitch fan blades to improve handling at ultra-low fan pressure ratios and to provide thrust reverse down to zero aircraft speed. The engine was aimed at ultra-quiet STOL aircraft operating from city center airports. In a bid for increased efficiency with speed, a development of the turbofan and turboprop known as a propfan engine was created that had an unducted fan. The fan blades are situated outside of the duct, so that it appears like a turboprop with wide scimitar-like blades. Both General Electric and Pratt & Whitney Allison demonstrated propfan engines in the 1980s. Excessive cabin noise and relatively cheap jet fuel prevented the engines being put into service. Terminology: afterburner, extra combustor immediately upstream of final nozzle, augmenter, afterburner on low bypass turbofan engines. Average stage loading, constant blade speed, bypass, airstream that completely bypasses the core compression system, combustor and turbine system, bypass ratio, bypass airflow/core compression inlet airflow, core, turbomachinery handling the airstream that passes through the combustor. Core power, residual shaft power from ideal turbine expansion to ambient pressure after deducting core compression power. Core thermal efficiency, core power equivalent of fuel flow, dry, afterburner not lit, EGT, exhaust gas temperature, EPR, engine pressure ratio, fan, turbofan LP compressor, fan pressure ratio, fan outlet total pressure intake delivery total pressure, flex temp, use of artificially high apparent air temperature to reduce engine wear, gas generator, engine core, HP compressor, high-pressure compressor, HP turbine, high-pressure turbine, intake ram drag, penalty associated with jet engines picking up air from the atmosphere, IEPR, integrated engine pressure ratio, IP compressor. Intermediate pressure compressor, IP turbine, intermediate pressure turbine, LP compressor, low-pressure compressor, LP turbine, low-pressure turbine, net thrust, nozzle total gross thrust, intake ram drag, overall pressure ratio, combustor inlet total pressure intake delivery total pressure, overall thermal efficiency, propulsive efficiency, propulsive power rate of production of propulsive kinetic energy, specific fuel consumption, total fuel flow net thrust, spooling up, accelerating, marked by a delay, static pressure, normal meaning of pressure. Excludes any kinetic energy effects, specific thrust, net thrust intake airflow, thermal efficiency, rate of production of propulsive kinetic energy fuel power, total fuel flow, combustor fuel flow rate, total pressure, static pressure plus kinetic energy term, turbine rotor inlet temperature, gas absolute mean temperature at principal turbine rotor entry, see also, jet engine, turbojet, turboprop, turboshaft, propfan, axial fan design, variable cycle engine, jet engine performance, gas turbine, turbine engine failure, notes and references. External links, Wikibooks, jet propulsion,